And its baseline energy would have been 3 from the harmonic oscillator, but it was shifted up by an additional 4.8 Hartree. So it had some upward shift, like I expected. Then I find 3 degenerate states, which were those p states, and you can see they are pretty degenerate. I guess I could have run it out. There's some problem in the last digit. I just didn't completely converge it. And they are shifted up from their nominal level of 5 by 3.9 volts, not volts, Hartree, which is, again, less than the shift from the S state, as you know, they always teach us in this atomic physics dogma, right? Well, not Eric's kind of atomic physics.
I do that kind of physics too.
Yeah, okay. Well, wait. Fancier than this. Okay. Then the D states, here they are, 5 of them. 1, 2, 3, 4, 5. Shifted up from 7 by yet less. And then finally, just as we expected, even though it's just a computer, it gets it just right. There's the last of these states. This extra S state is shifted up by a bit more than the other D's, just as we had expected. Any questions here? Now there's one interesting subtle thing in the data. If you look at these D states, which should be degenerate by spherical symmetry, they are, you'll notice, and it's not just noise in the last digit or two, there's definitely a grouping of 3 and a grouping of 2. Can someone tell me what that is?
You asymmetric, were you non-isotropic? Can you grid?
Well, it could be from anisotropic resolution in the grid, but in this case, I believe it's another effect that's quite real. There's something called EG and T2G. This is the classic crystal field splitting, right? Because I have periodic images of these guys, right, on a cube. And these are D states. And that's what happens, right? But I don't have to know anything. Yeah, Katie's a chemist, so she picked up on that. I don't have to know any fancy chemistry. I just calculate the thing. No, it's nice to understand. But. So it's just, I think, very neat that these things come out the way you should expect. Now, let's look at the states. Yeah.
So that's the difference in the crystal. The ones that look like jacks behave differently than like the donut ones.
Yeah. Yeah.
Oh.
Shall we look and see? Here we are. So this is a slice through the first wave function. This is the S wave function. M1 just tells you which plane it is, right? It's the X plane. And that looks pretty spherical. Just a little proviso here. This was not done on a uniform grid. This is still the silly 20 by 25 grid by 30. So the data set's a little longer in this dimension than this dimension, even though it represents the same space. I just have more grid points in one direction. So in my plotting routine, it actually looks a little elongated, but trust me, it's a sphere. And then if I look at my next plane, another slice, perpendicular, sure, spherically symmetric S state. State number 2 should be a P state, right? Now, there's a little subtlety here, which is that the way my imaging program works, it takes a slice through the data set, it looks at all the values, and whatever they are, the maximum one, it recodes up to the brightest you can have. So what we're looking at here, this actually is a nodal plane. You'll see it in the next slide coming up. This is a nodal plane, and there's just some noise left over, and there's a little bit of activity in that plane. But if we look here in this plane, you can see that the nodal plane was the X plane I was looking at before, cuts in this way. And what I have is your classic P state from your chemistry textbook. And now we're going to slice the other way through this guy. Let's see what we get. Right? Nice P state. You don't have to know any chemistry, it just comes out of it. The next state up, in this plane, he looks like a P state already. Right? And then, we slice through the other planes. Good. P state. Third P state stuff. Okay. Now, D states, we hope. Not cutting quite through the right plane on this one. But, nope, not through that one. There it is. Right? So the two planes we were looking at before were this plane and this plane, which really are nodal planes. It just was, again, the way the plotting amplifies the brightness. And you'll notice the crystal field splitting. This is the lowest energy D state. And these lobes here, right, are not, the nearest atom is right over here along the coordinate direction. Whoa, where'd he go? I'll use this one, right? Right. The nearest atoms are in this direction, this direction, this direction, and this direction. And you can see they are avoiding those other atoms. Which makes sense. Okay, then, whatever, we can go through. There's, again, this one looks just like the previous one, but it's oriented on a different axis. Here's another one of these fourfold looking guys. And then the claim was, then we have the mushroom cloud looking ones. All right. Oh, wait, this is still psi 8. Sorry. Oh! I missed it. Can't go back, but the next state has the same feature. See? All right, that's your classic D state with the two things on top and the donut hole around the middle. And if I slice, in the next slice, you'll cut through the donut hole. Wait, no, not that one. Where's it? Oh, now I'm up to the second S state. This is the top state. And you can see, it's nice and spherically symmetric. It's got a node in the radial wave function, as you should expect, and a little ring out here. It's a little hard to see. If you come look at the screen later, you can really see that. And then it's the same way through the other thing. So I just think it's so neat that, like all those pictures from the chemistry book, yeah, they're really real. I never would have believed it, but they are. Okay, and then that cycles back around. Okay, so that is when we do the harmonic oscillators and the quantum dot. Now let's look at the hydrogen data set. So what you do for hydrogen is we calculate the energy at a series of separations. And I have the data. Here's the graph of my data. So what I'm showing you here is the separation between the two protons in the hydrogen molecule on the horizontal axis. The vertical axis, I have a typo, shoot. This is the binding energy of the molecule. It's the total energy of the molecule minus twice the energy of a single hydrogen atom, which is, one single hydrogen atom is 13.6 volts. That's half a Hartree. So the binding energy is minus half a Hartree. There's two of them, so I'm really subtracting off minus one Hartree, not 2 times minus 1 Hartree. That's just, I flipped a bit in my head. But this is the potential then as a function of that separation. So you can see then the minimum energy separation is somewhere around 1.4 atomic units, about 0.7 angstroms. The energy here is the binding energy of the molecule, is around, it's about 1/10 of a Hartree, a little more, so maybe 3 volts. And then the curvature down here gives me the vibrational frequency. And you can just calculate that on the next assignment. Here I'll show you the results. I'll clear the screen and then put the results up. So here's the bond length. As I said, it was about 0.7 angstroms. It actually was 0.768. There's the experimental value right out of the CRC handbook, and the error is about 4%. The spring constant, which controls the vibrational frequency, is off by about 6%. When you take the square root to get the frequency, that'll be off by 3%. It's pretty good, I think. And the binding energy I said was, around a little more than 3 volts. That's off. Those are usually worse. But you can actually do hydrogen on the next assignment. I think that's pretty good. Okay. Last assignment then would be the germanium crystal. So let's see what you'll get for the germanium crystal. More GE.text. You can calculate the cohesive energy off the assignment. This is just a sketch of the calculation. Basically, you calculate an electronic energy, the Ewald energy, for a cube containing 8 atoms. So this is the total electronic energy of those 8 germanium atoms. Per atom, it has this much energy in Hartrees. You then do an isolated atom calculation, which has this much energy, which is less magnitude but higher because it's a negative number. So the energy is lower to go from the isolated atom to the atom in the crystal, which is good. The crystal hangs together. It's lower by about this many Hartree. which in volts is 4.4, and the experimental value is not too far off. It's about 13% off there. Now these are very primitive calculations you're doing. They're real, but we haven't integrated over the Brillouin zone nicely. There's lots of stuff flowing through, but it comes out pretty realistically. Now the germanium that you can do in the assignment, I want to show you some pictures of everything. The germanium exists in a diamond lattice, and that's based on an FCC lattice. So I'm going to show you the electron density in germanium. So the crystal looks kind of like this. There's a cubic cell that we've calculated with, and it's FCC. So as you got all the corners of your cube, and then you have all the face centers also. And then there's additional structure in the diamond lattice where there are atoms that are off this plane. So what I'm going to show you are the charge densities sliced through this plane, the FCC face, and then through a diagonal plane that looks like this, through the crystal like so. And in that diagonal plane, you can actually see the atom to which the corner atoms are bonded to. Because I want to see what the bonds look like also. Ah, sorry, all right. I just think that's remarkable. You're getting like the real binding energy out of this thing, which you guys can make for yourselves. Okay, where are these? So here's the 100 face. So the atoms are centered on the corners in this calculation, as you can see, and then an atom right in the middle of this face. Now, something looks a little odd, which is that the atoms don't appear like high-density regions. They appear like low-density regions. Can anyone tell me why they're low-density? Someone not from my group. Yes?
I'm not sure. So you replace the core electrons in nuclear ones by a pseudo-potential.
By a potential, exactly. And as a consequence, those core electrons are not there. So the core electrons are basically missing, and that's why you don't see them, right? So the core looks black. The remaining valence that was bad. I don't want to hit that X. Persistent little thing. The valence electrons, though, outside the core, they make a nice spherical shell. You can see there's some activity kind of between them, but that's actually going out of plane. So what I want to do now is show you the plane, this plane, slice through, it's a little hard to see here. This plane here, which will cut along the long diagonal of that cube. You'll see the same corner atoms, but you'll see additional atoms on the inside where the bonds occur. I don't know how good this is going to come out with the lighting in here, but we'll give it a shot. Right. So these are the corner of the cube, these two. Then you go across the long diagonal here, and this is the other corner of the cube. And so you have your atoms on the corners, and then you have the additional atoms on the inside of the cube that I was referring to. And you see a nice buildup of charge right between them. And this is actually the chemical bond between the two neighboring chains. There and there, and then this chain and this chain.
What's our resolution?
What's the resolution meaning?
Of the data?
Oh, the data here?
This is smooth, right?
This is, I think the original pick, what was the FFT box on this guy? No, I don't remember. I think it's like on a 32 cube set. And definitely to make it this big on the screen, I had to stretch it out and smooth it a little bit. Exactly. Okay, well anyway, there's a picture of your chemical bond. If you ever want to know what one looks like. You can actually calculate it for yourself. You don't have to take my word for it. But that's what it looks like here.
So why is the top layer not interacting with the bottom layer? Oh,
it's not bonded to it. Right, exactly. Yeah, that's basically what you have to kind of look at the diamond lattice structure. What is happening is that, okay, these are tetrahedrally bonded. So the tetrahedral bonds, you've got these two tetrahedral bonds going down like this. The next two tetrahedral bonds go up like this. So they orient up, but then there's a rotation 90 degrees out of plane. So there's another layer of atoms here, along here, which is out of this plane. And then those are bonded to these atoms. You kind of see some of the, well, you can't really see. Those are bonded to these atoms here. I mean, these mysterious out-of-plane ones I'm talking about, they're bonded to these atoms here and to these atoms here. And that cross-links and then gives structural stability to the crystal. Now, if you do the assignment, you can slice for yourself. Yeah, excellent, good. Other questions? All right, so that then wraps up our course. I hope it's been fun for you guys. I've hoped to emphasize the fact that in computing, again, the big advances come from the thinking, not necessarily from the numerics. But the numerics are very important. And if you want to make your life easier, you want to be very careful how you do your coding, right? And think through the physics from the beginning, and better yet, try to find some intermediate language that you can think in terms of, for which the computer can also take as well, to minimize the torment of debugging, because you can lose a lot of hair pulling on it, trying to debug the code. Okay? All right, did you want to say anything, Eric, on your...
I'll be starting on Friday, semi-classical methods. It'll be a lot of fun. Tell all your friends.
Voila. All right, thanks, guys.